Alrighty, so day one's topics, stem and leaf plots. When I said that, did a little bell go off somewhere in your brain where you're like, I think I've heard of those before? Okay. How about sample size? Do you remember talking about sample size? Okay, some no's, some yeses. Correlation versus causation. Okay, a few people saying yes. Probability. Yeah, I mean, you took a whole class on that, right? How about expected value? Okay, the words themselves, a couple of people are yes, a couple of people are no, and that's what happens because you haven't done this in a long time. So we need to talk about those, not because they're difficult, but because we forget stuff. When you don't use it, you lose it. That's how it is. So this says we're going to make a stem and leaf plot of the following data. And a stem and leaf plot always starts with a vertical line. And then what you do is you figure out how you could represent the numbers that are up there by putting most of it in the front, which is the stem, and only putting one number in the back as the leaf, because that's the rule. The leaf always has just one number. So I realize, well, the numbers I have here are all in the tens. In fact, I have 10s, 20s, and 30s. So if I just put a 1, a 2, and a 3 up there, and I use that as if it were tens, then I'm going to be able to represent all of the numbers that I have up here. But you got to kind of stay organized. So let's see. We have to put these in order to stay organized, and that means I better go find all the stuff that starts with a 1 in the first position. So that'd be that one, that one, that one, that one, and one hidden back there. And like I said, we want to represent them in order. We already have the 1 taken care of in the front. So what we do is we look at what's in the ones digit, and that would be a 1, a 2, a 3, a 4, and a 5, and that's what we write down. So we just figured out a way to represent those 5 numbers using one number in the leaves, and everything else goes in the stems. Now, because I don't like not having things organized, what I'll usually do is put a slash through the ones that I've already used, because sometimes they give us a ton of numbers, and it's difficult to remember, okay, which ones did I already write down and which ones didn't I. But just a slash, no scribbling, because you want to be able to go back and double check everything. Now I need the stuff that had the 2 in the front. Let's see, 21, 23, 23, 26. Did I miss any? All right, so let's put that in order. 1, 3, 3, 6. And then go after everything that has a 3 in the front. So 33, 4, 5, and 6. That looks like that's it, and they're all in order already. 3, 4, 5, 6. And then because sometimes I miss one, just because there's lots of them, I will always count and make sure I have them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Thank you. And down here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Got them all. But this isn't going to mean anything to anybody if we don't put a key. We have to tell people what we're trying to do. And it doesn't have to be an example from your stem and leaf plot, but I like to do that because I think it helps people. So I would show them that a 2 and a vertical line and a 3, and then an arrow shows them means. So 23 is represented by 2, vertical line 3. And that way, anybody should really be able to look at the key and go, oh, now I know what these numbers are. Now, why do we do that? Not for the mean. They're going to ask you for mean, median, and mode. Do you remember what mean is? Okay, add them all up, divide by how many you have, because that we could have just done without having them in order like this. But the median is the middle one, and since we put these in order, this would be really helpful to find the median. And there were 13 of them, 13 divided by 2 would be 6.5. That tells me there are 6 in front of it and 6 behind it. So it's right in the middle in the 7th position. 1, 2, 3, 4, 5, 6, 7. 23 is my median. The other thing it's really good for is the mode. What's the mode, everybody? Mean is the average. Median is the middle one when they're in order. What's mode mean? Most. The one that's there the most. This is also a really good way to see, hey, there's 2 of these 3's here. 23 is the mode. It's there twice. So for median and mode, this is a really good way to display data. It's just a matter of getting it all organized first. So they might ask you, they're probably going to give you the stem and leaf plot, and then they'll ask you a question like, what's the median of this set of data? So you're going to have to go down and read the key, and then count how many pieces of data you have and figure out which one would be right in the middle. Now, if there's not one right in the middle, remember you have to average the 2 middle ones. So you add them together and you divide by 2, and that'll get you the median. So, question for you. This one is just like the one we just did. Do we need to do this one? Anybody feel like we should do one more of those? All right, so let's go on to something that's a little tougher, and that's called a back-to-back stem and leaf plot. And it's a way to, if you have a question that you're asking 2 separate groups, it's a way to keep it organized all in one stem and leaf plot by making a back-to-back stem and leaf plot for this data. So what I'm doing right now is I'm looking at the girls and the boys, and when you do a back-to-back stem and leaf plot, the stems go right in the middle. And I'm trying to see what kind of numbers are we talking about here for both the boys and the girls. And I see it's 10s again. Looks like 11 is the smallest number from both sets, and 51 is the biggest number from both sets. So again, my stems need to be everything but one number. So I'm going to need a 1, a 2, a 3, a 4, and a 5 to represent all of this data. And then I would do the girls first, because the girls side is going to go on the right, and I just label it girls over here. And that's going to look just like the stem and leaf plot we just did on the last page. But again, the more data they give you, the harder it is to keep organized. So let's go through and underline anything that has a 1 in the front. I have 5 of them. Is that what you got? Okay, so let's put them in order. 1, 3, 4, 4, 5. And put a slash through them. Make sure we have them. All right, 2s. Ooh, there's a lot of them. 1, 2, 3, 4, 5, 6, 7. Did I get them all? Okay, so 22, 22, 2 and 2, and I'll cross those off. 3, 4, 5, 7, and 8. And then go after the 3s. What do we have? 3, 3, 4, 4, 4, 5. And again, there's a lot of data here. 3, 3, 4, 4, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Whew. So the girls are taken care of. Now, here's where it gets weird. We have to put the boys' data on backwards. Back-to-back stem and leaf plots are written from the inside out. So, go over here for boys. Nothing with the 1s. 2s. One, 2, 2, 2, 3, 3. So inside out. All right, threes. 34, 36, 37, 35. Got them all? 4, 5, 6, 7. Forties. 3, 3, 4, 5. And 51. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. And this is even worse without a key. Nobody's going to know what on earth we're talking about if we don't put a key down there. So again, I try to pick something where it does have something represented from the data that we have. So I might pick something with a 2 or a 3 this time. I think I'm going to pick a 3. And let's see, going out this way, we could do a 4, and out that way a 5. And then arrows outward to show, hey, if you read it this way, this is going to say 34 for the boys, and this is going to say 35 for the girls. Same thing, very helpful for finding the median. You know, if they ask you the median for the boys, you go up and you say, oh yeah, there was 15 of those, so 7 in the front, 7 in the back. The 8th one is the very middle one, you know. Median and mode, these are very, very useful for. And that's the reason you'll see those. Sample size. Sample size is the number of pieces of data that you collect. We were talking last hour, somebody remembered the sign in Elk River now is like 23,000 something. So if you went and asked 5 people a question about something in Elk River and said, I'm going to make a survey out of this, that doesn't make any sense. We've got a lot of people. You have to ask a lot of people. And in province stats, you talk about, you know, what's the cutoff supposed to be, and really that's more about AP stats also. What we want to know is, are you able to read through a situation and say, that's not enough data, they shouldn't be making a survey based on that. So the larger the sample size, the more reliable the results. If you could ask everybody in Elk River the question, that would be a fantastic survey. But that takes a lot of time and money, so most people don't do that. So this says Doug attends a school with a population of 4,554 students, always trying some kind of get-rich-quick scheme. He decides that he wants to try to sell his mother's pickled beets right before lunch each day. Everybody's hungry. They should want the beets. He asks his 4 closest friends what they think of the idea. They tell him they think it's a great idea because they all love his mother's pickled beets. Doug decides to try to sell the pickled beets. Is Doug's reasoning sound? No. This school had, I don't want to scroll back, what it was, 4,554. He asked 4 people. No. Ask more people. Secondly, his friends might not want to hurt his feelings. Maybe they can't stand his mom's pickled beets, but they know he would go home and tell her, and she's going to be hurt. So they might not answer, well, unfortunately, honestly, you know. So ask people that aren't your friends. And that's the kind of stuff that if you do still go to malls, every once in a while there's somebody standing there with a clipboard and you try to avoid them like crazy, but they have questions they're supposed to ask people, and those are survey questions that hopefully are going to help them know whether or not they should, do business. Actually, I was just thinking about the fact that they're talking a lot about pet stores now. Some of the states have decided that pet stores should no longer be able to sell actual pets, and that's because they come from puppy mills, and so a lot of them are closing down, and there's only 1 or 2 left in the state right now. Northtown has one, and I think it was somewhere near Rosedale where there was another one. And so, who knows whether or not they're going to be able to stay in business. And they might want to just send somebody out with a clipboard and say, do you have a problem receiving a puppy from a puppy mill, something along those lines, to see if people care or not. Or maybe they're just happy to get the dog and they don't care. They just want whatever puppy. But those are the kinds of questions that if they want to stay in business, they need to do. Way, way, way back when. Did you guys know that we had a Wendy's in Elk River at one time? Yeah, we had a Wendy's in Elk River, and it was over by, by Pizza Ranch where that bank is right there. We had a Wendy's. And due to poor management, Wendy's went out of business. And before Taco Bell even started, Target used to be over there as well. It used to be where Furniture Mart is now. And they had people standing outside of Target, and they would ask, if there were a fast food restaurant place to come to Elk River, what kind of food would you like them to have? And if people answered, then they had a follow-up question. Which particular restaurant would you like to go to? And people in Elk River said Mexican food. Didn't have a lot of Mexican food places at that time. And they said, of the choices for Mexican food, what restaurant would you go to the most? And people said Taco Bell. And Taco Bell has been doing good business in Elk River ever since. It's asking the right questions to figure out how you can make your living, how you can make things work. So there's two fancy words that show up when you talk about statistics, and that's going to be correlation and causation. Correlation means we did the math, and the numbers show us that two pieces of data have some kind of a mathematical relationship. Now, it might just be dumb luck, because sometimes that happens. Math does crazy things. So sometimes we see there's a mathematical relationship between two extremely bizarre things. And that doesn't mean they cause one another. Causation is more logical. That's where two pieces of data actually show there is a mathematical relationship. One appears to cause the other. Before a medication can come out, they have to have what are called blind trials. And that's where people come in that have whatever ailment is that they're trying to cure or fix. And they have people that are in what's called a placebo group. And those are people that actually don't get any medication. They think they're getting medication, but they're not. And then they have a group of people that actually receive their medication. And what they're hoping for is a dramatic change in the people that receive their medication for the better. And if that happens, then usually we see a new medication come out on the market. That's causation. When they got the medicine, they got better. When they got the medicine, their symptoms subsided. That's causation. So dumb luck is correlation, whereas causation is, hey, there's a logical reason for this. So correlation or causation. There has actually been shown that there's a mathematical relationship between women's skirt lengths and the stock market. Apparently, when the stock market is doing well, women's skirt lengths go up. Mini skirts come back. Shorter skirts come back. Do you believe that the stock market climbing causes women's skirt lengths to go back up? No, that's not logical. This is correlation. Now, we could try to reason logically and say something like, maybe it's because when the stock market is doing well, people have more money and they're more fashion conscious, so maybe they go out and buy more clothes than get into those things. But it's just a weird mathematical thing that's happened, and it is. It's been proven. There is a mathematical relationship. Bless you. Benadryl, which generically is called diphenhydramine, and relief of allergy symptoms. Does taking that medication relieve your allergy symptoms? That's causation. That's logical. And that's been around long enough that there is absolute proof that, yes, that's the reason you're feeling better. It's because you're taking that. Ice cream sales in the U.S. and shark attacks. Correlation or causation? Correlation. That is another proven mathematical relationship. So you think, okay, we eat more ice cream, we're tastier to the sharks. Must be it. No, again, you try to think, well, if we're eating more ice cream, it's probably because it's hotter outside. So it's hotter outside, we're eating more ice cream, there's more people in the water, there's going to be more shark attacks. So there's a correlation, but they don't cause one another. Now this last one, gasoline prices in the speculators market. And I'm going to flat out tell you that one because most people don't know anything about the speculators market. This is actually causation. Now, every year when we get to summer, we're going to hear on the news, it's supply and demand. More people are on vacation, more people are driving, so they need more gas, and because the demand is high, we can charge what we want to charge. That's a bunch of baloney. It's actually all set by a group of old wealthy men called the speculators market. And what they do is they sit down and they look at the political climate of every country that has oil, and they talk to seismologists about earthquakes and things of that nature, and they make predictions about what they think is going to happen. They really are trying to predict the future. And if they believe something bad is going to happen, oil prices go up. If they don't, oil prices can stay the same or they can go down a little bit. So it's the speculators market that really sets our oil prices. So it isn't supply and demand, although everybody always says that. All right, example 7. Jelly beans. Everybody, it's jelly beans and socks. You hear about those a lot on the MCAs and the ACTs. There's a jar of jelly beans on the shelf. Contains 12 red jelly beans, 16 purple jelly beans, 15 yellow jelly beans, and 17 green jelly beans. What is the probability that you will reach in without looking and choose a purple jelly bean? Well, probability is all about counting what it is you want to happen. How many are there that you want to happen? And dividing that by the total. So what we want to happen is we want to get a purple jelly bean. How many purples are there? 16. And I can see you're already typing it in. Did anybody already get the total? 60, 60. So reducing that, let's see, 4 will go into both. We could reduce it to 4/15, but usually they put it as either a decimal or a percentage. So 4 divided by 15, so you could see it as 0.26 repeating, or if we move the decimal over 2 places, 26.6%, because that's what you always do with percentages. You move the decimal over 2 places. Oh, I should put my repeating line up there. They might even round it 26.7%, something like that. But you'll know it when you see it. So you want to kind of look at the answers and say, all right, what are they doing here? All righty. This one says, what's the probability you're going to reach in without looking? You're going to pull out a green jelly bean, eat it, and then reach in and pull out a red jelly bean. Now that word and is important in probability. And usually means multiply. So in this case, we're talking multiplication. That's because we want both things to happen at once. So let's see here. We need to get a green jelly bean. How many greens were there? 17 out of 60. And so we're going to multiply. How many reds? 12. But you ate one of the jelly beans. So how many total? 59. And let's see, maybe that reduces to something halfway decent, huh? Parentheses, 17 divided by 60, parentheses, 12 divided by 59. Math number 1. You'd probably see that one as a decimal. Usually when the numbers get bigger, they go to the decimals. So this would be about 5.8%, moving that decimal over into 2 positions. Jelly beans, and multiply. And this without replacement, you have to watch out for that. You have to realize, okay, so I took one out, now the total is different when I go through. Alrighty, they love the next ones. They love the dartboard ones. And that's because it requires that you know some area formulas. So they're trying to make sure you know your area formulas. Using the figure below, find the probability that if you are equally likely to hit anywhere on the target, you will hit the outermost ring of the target. Well, first I better know where the outermost ring is. That's that one. Right there. Okay. So probability is what I want to happen. I want to hit that ring. That ring is two-dimensional. So I am talking about area. Do you remember area of a circle? How do we get that? Area equals pi r squared. You are going to get a formula sheet for the MCAs. And that typically is one of the formulas that's on there. All right, so now here's the deal. I just want the area of this ring, but I can't get that. So I have to figure out, how do I get just the ring? It's kind of like a donut. So let's see. If you want to make a donut, you cut the big one out, and then you take a smaller one and you punch it in the middle and you remove that piece. That's subtraction. So if we take the big one that has a radius of 2, 4, 6, and subtract that donut hole in the middle, 2, 4, that'll give us the area of our ring. So that's going to be 36 pi minus 16 pi, which is 20 pi. Now that's what we want to happen. So that's going on top of our fraction. And it did say we're not so bad that we're going to miss the target. They said no matter what, our dart is going to land on that. So what shape is the outside of the dartboard? It is a square. And that's going to be area equals side squared, or 20 times 20. Which is 400. Now we absolutely will not see that as one of the answers. They're going to want to make us punch that in and make sure we know what it is. So parentheses, 20 times pi, parentheses, and then divide it by 400. 0.157, approximately 15.7%. So a pretty good chance that we'd hit that outside ring. Now, what's more likely? I haven't played darts in a long, long time. Down here it says, using the figure below, find the probability if you're equally likely to hit anywhere on the target that you're going to land on the outside border. This stuff right here. Yeah, if you haven't been playing darts regularly, that's probably where things are going to land. So now we kind of have to use our donut example to figure out what the area of that shape is, because this is not any shape we know. I mean, one of the edges is straight, but the others are circles. So can somebody tell me how we could figure out what the area of that shape is? Square minus the big circle. Absolutely. So we need the area of the square minus the area of the big circle. That's what we need. Well, the area of the square is 28 by 28. And the area of the circle, 3, 6, 9, 12, is going to be pi times 12 squared. All right, 28 times 28. Most people don't have that memorized. 784. So that's what we want to happen. We don't really want it, but that's what we were focusing on for the problem, because we don't get any points for hitting there. 784 minus 144 pi over the area of the whole thing. Didn't we find that when we were doing our math? What's the area of the whole thing? 784. So if we just throw a couple of parentheses on the top of there, we ought to be able to get ourselves a nice little probability for them. 784 minus 144 second pi, parentheses divided by 784. So 0.423, or approximately 42.3%. Yeah, that's a pretty high percentage. If you haven't thrown darts before, you're probably going to end up on that outside ring. And there it is. Now, the next one, neither class remembered the name of. But once we did it, they're like, oh yeah, this makes perfect sense. Expected value is really just weighted grading. You know, it's like you do for each of your classes. So expected value is using a weighted system to find the number that should be expected. For example, you've scored an 85 on your first test, a 78 on your first quiz, and 100 on your homework. Tests account for 70% of your grade. Quizzes account for 10% of your grade. Hunter, put the phone away. And homework accounts for 20% of your grade. What is your overall grade? So what you do is you take each of your scores times the percentage of your score that comes from that. So 85, that was for your test. And it's set up there, tests account for 70% of your grade. Now notice you have to put it back as a decimal. So 70% becomes 0.7. 78 came from quizzes, 10% of your grade. 100 came from homework, that's 20% of your grade. And when you multiply all that together and add, you get 87.3. So that would be your overall grade. So expected value, just think weighted grading. That's what expected value is, weighted grading. So this says, let's find the expected value of the ticket sales below. And I don't see anything here that says, what do we get for a percentage for these? That's because we have to figure that out. So we have to figure out 30 out of what, 25 out of what, 10 out of what, so that we know what those percentages are. So let's see, 30 and 50 is 80, we got 90 total. So this would be 30 out of 90. That'll reduce to 1/3. 25 out of 90. 18, 5/18, and 25 out of 90, 5/18, and 10 out of 90, which would be 1/9. Now you wouldn't have to reduce. You could just use the first fraction if you didn't want to bother with it. But what I need to know is 6 is going to happen 1/3 of the time, 8 is going to happen 5/18 of the time, so is 12. And 20 is only going to happen 1/9 of the time. So if those are the realities of what can happen, what should we expect to have to pay so that we don't, like, sometimes you can really get way too much. I'm not even going to call and get the tickets because I'm afraid they're going to be too much money. And sometimes you can underestimate, and you don't really want to do that. You want to know, what should I expect to happen here? So 6 parentheses 1 divided by 3 parentheses plus 8 parentheses 5 divided by 18 parentheses plus 12 parentheses 5 divided by 18 parentheses plus 20 parentheses 1 divided by 9 parentheses. $9.78. Double check so I make sure I didn't punch something in wrong. Yep, $9.78. Now, you can argue, and you would have a really good argument, but Cedar Home, that's not the price of any of these tickets. No, but it means probably somewhere between these two is where you have your best chance. And we already knew that by looking at the 25 out of 90. We knew that was your best chance of getting tickets, were the $8 and the $12. So if you expect around $10, you're not going to feel so bad when they say, well, all we have is $12 tickets. You should be okay. Alrighty. Same type of thing for this one. We want to find the expected value of the ticket sales that we have down here. So what should we do first? Let's add them all up. 60, 70, 89. Ooh, this one came out pretty. It's 100. So we have 40 out of 100, 20 out of 100, 20 out of 100, and 20 out of 100. I definitely would reduce those. And again, we're going to do expected value. So money times probability plus money times probability, money and probability, money and probability. So let's see what we get. So you kind of see why they call it expected value instead of weighted grading, because these two problems we just did weren't about grading. But that's what you need to think of. So $8.60, which again is not one of the options, but it would give you time to prepare and say, okay, so if I expect to spend around $9, it's probably going to be the $8 or $10 tickets that I'll be able to get. And just kind of prepare yourself and be ready for that. Now, I know we have time in here, but we didn't because of some interruptions in second hour. So I think we're just going to hold off on 12 and 13 until tomorrow. That way the two classes can be in the same spots. And